So again, let's look at this soft switching from conceptual point of view first. Does that make sense, what we're trying to do here? We can avoid having the overlaps by not having the overlaps, of course, right? Which is smart, in my opinion. It is clever, right? If you can do something like this. And what's even more awesome about this is that you'll see later on that the way to achieve this, and of course the answer to this, it is possible to get this, but the way to get this, the way to be able to prevent overlapping of the voltage and current is done through a very, very simple circuit. One reason why, I think I mentioned this in EE411 maybe multiple times, I'm going to say it again, is that one of the reasons why I fell in love with power electronics, because in power electronics, majority of the techniques that we use utilize simple concepts, utilize simple circuits, right? And to achieve big things, such as this one, you'll see. Okay, you'll see that a simple circuit that you learn in 211, right? We're going to use it here to achieve exactly what you see on the screen, right? To be able to not have voltage across the switch to overlap with the current. Okay, so that's why this is one of my favorite topics in power electronics, is to go over soft switching. Okay, so that's the concept behind soft switching. Any questions? Right. Okay, now before we go over the topology, let's go over the basics, of course, in terms of how can we achieve this, right? I've already mentioned that in soft switching, we want current to go to zero, right? And we wait until the current to go to zero before we turn off the switch, as an example. And we do the opposite for turning on, of course. Now, how do we achieve this, right? How do we make the current to go to zero, right? Well, if you have a square wave current, right? If let's say you turn on the MOSFET, like in PWM, you turn on the MOSFET, and then the current through the MOSFET is going to be pretty much flat, right? And then you turn it off, and it's going to go straight down. Of course, you're not going to get that kind of a property of a current going to zero slowly, right? The change is fast, right? The change in the current is fast if you keep, square wave type of current. However, if you can somehow incorporate a sine wave, right, as the shape of the current or voltage, right, then again, conceptually, it should be possible to achieve this, right? Because a sine wave, as you know, right, a sine wave, as you know, right there, right? If let's say current has the shape of a sine wave, then that current will go up, right, from 0 amp, will go up to its peak value, and it will naturally go to zero at some point of time, right there. It will naturally go to zero. And this is happening without us forcing the current to go to zero, right? So if you can somehow manipulate the components in the circuit in such a way that when the switch turns on or conducting, the switch current follows a sine wave, then naturally or inherently, that current through the switch eventually will go to zero, right? And then when that current goes to zero, then that will be the perfect time for us to turn off the switch at zero switching current, zero current switching, what do you call it? Zero current switching transition, which means B times I is going to be zero, right? If the current goes to zero, doesn't matter what voltage you have, B times I is going to be zero, right? So does that make sense? So that's kind of the approach here, is that instead of rather than using a square wave type of current, right, you turn on the MOSFET and the current is flat. What if we can somehow shape the current through the switch to be a sine wave, right? To be something like this, right there. Okay, that way it goes to zero, naturally go to zero. Okay, so that's the approach. Now, that's the strategy. So then, how do you do this, right? That's next. how do you actually have a DC circuit? Because we're dealing with DC to DC, right? And a sine wave is not a DC, as you can see, right? A sine wave, right? You have plus and minus there, right? Right, sure, but then if you can somehow, let's just say, do only the positive half of the cycle, right? Then we have a DC, right? If we can somehow clamp the negative portion, then we have a DC current, not AC, right? So keep that in mind, even though in terms of the concept, you want a sine wave, but we could somehow just make use of half of the cycle, either positive or negative, then we end up with a DC current, okay? Now, again, what circuit do you use to produce this, right? How do you produce a sine wave from a DC? Right away, you take the inverter from say it again.
Half-wave rectifier.
Full wave rectifier. Well, full wave, the input is AC, the output is DC, right? In this case, we have DC input, but then we want to create sine wave within the converter, right? So the input is DC, right? So the input to the converter is DC, but then we want to create a sine wave inside the converter. How do you do that? Well, you're not going to be using inverter because that's going to be too much, right? As you remember from EE411, you still remember, in order to get an inverter, you need at least 4 switches, right? That's too much, right? So what can we do? Well, this is what I was referring to, right? Reason why I fell in love with power electronics. Again, I'm going to mention this because we are using simple concept to gain big advantage, right? So do you remember this circuit right here, resonance circuit? Yes or no? Anybody remember this, learning about resonance circuit?
Yes.
Okay, what class is that?
212?
212, exactly. 212, you learn about resonance circuit. And resonance circuit consists of energy storage components, right? Resonance circuit can be constructed from at least 2 energy storage components, right? One is inductor, the other one is capacitor, right? And that's what we're going to use for this, right? The simple circuit that you learn from EE211 or 212, we'll try to use it to achieve this, right? How so? Well, let's take a look. Let's check this out. I'm going to go over 2 different types of basic resonance circuit. The first one is called series, and the second one is parallel circuit, right? You probably remember those from 212. Here's an example of a series resonance circuit, right? Very simple, isn't it? You only have L and C in series. No, sorry, they are in series, right? They're connected in series. And this voltage right there, the source, right? That's DC. This is a DC source. And you learn that if you have a DC source, right, and then you connect it to an ideal inductor as well as an ideal capacitor, then what's going to happen? That's why you learn about differential equations, right? One of the calculus courses that you took at Cal Poly is differential equations. And you learn that this type of circuit gives you a second order system, right? And when you analyze the circuit, derive the equations, I'm not going to, well, I'll do that here again, sorry. You'll see that what's going to happen is that even though the input is DC, right, the current that you have in this circuit will be sinusoidal, right? How is that possible? Well, because you have 2 energy storage, right? And these 2 energy storage, they take turn in terms of storing and releasing energy. So at some point of time, we are storing energy to the inductor, right? And then this capacitor is discharging this way, right? And inductor is charging. And then at some other time, inductor reverses, right? Now inductor releasing its energy, and now charging the cap while the cap is discharging. Oh, sorry, while the cap is charging. So it's always the interaction between the two, right? Complementary action between the two. If the inductor is charging, the capacitor is discharging, and vice versa, right? So charging, discharging, charging, discharging. So by me moving the cursor here, charging, discharging, charging, discharging, you can see that the current that is associated with that kind of action must be back and forth current, right? It's not going to be flat current. It's going to be back and forth, back and forth, back and forth, right? And if you derive the mathematical equation, which I will pretty soon here, then turn out to be that the current that you have in this circuit, as you learn from 212, is going to be sinusoidal. It's going to follow a sinusoidal shape, right? At what frequency? Do you remember?
1 over square root of LC.
1 over square root of LC. What unit is that?
Hertz, or radians per second.
Yeah, so be careful. This is radian per second. What if you want hertz?
Goodbye.
Yes. See, now you remember, right, that if you have a resonance circuit, then you're going to end up with a sine wave of the current through this loop, and also sinusoidal shape of the voltage across the cap, right? And as well as voltage, sinusoidal voltage across the inductor, right? So if you look at the inductor itself, voltage across is sine wave, current through it is sine wave. Same thing with capacitor, current through it is sine wave, voltage across it is sine wave. And so I simulated this before I derived the equation, right? And you can take a look at the resulting waveforms, right? That capacitor voltage is sine wave. See that green waveform? That's a sine wave. And then the red waveform, the dashed line, that's the inductor current. It's also a sine wave, right? Now, this is an important property, right? Because remember what we want to achieve with soft switching? We want our switch current or voltage to follow a sine wave. Imagine if I have a switch right here, right? A MOSFET, right? That is connected in series. Then you can see that current through that MOSFET must be the same as current through the inductor, right? And must be the same as the current through the capacitor. And guess what the shape is for that switch current? It's going to be a sine wave. Clever, isn't it? I think so. I mean, it's very simple circuit, but then we are able to actually get the shape of the switch current to be a sine wave. Now, what if you connect the switch across the capacitor? Right? And of course, the voltage across that switch must follow a sine wave, the green waveform right there. Right? So cool, in my opinion. Right? So then let's look at the equations for this, okay? So as I said earlier, if you have that simple circuit, the math behind it is not that simple. Of course, it's differential equations, right? And this is just to prove that the resulting voltage and current will be sine wave, right? These are just one way to prove that we're going to end up with sine wave, current, and voltage, right? Through the mathematical equation. So that's what I have here. If you look at KVL around the loop, right? That's a simple loop, right? Voltage source equals voltage across the cap and voltage across the inductor, right? That's one equation. You can see we have one equation, two unknowns. What are the unknowns? IL and VC, right? We typically know L and we will typically know VS, right? That's the first equation. So I have one equation, two unknowns. So I need another equation. By KCL, I know that IL is equal to IC, right? Because they're the same current. There's only one loop. And IC, as you learned from 211, is equal to C dVc dt, right? So now if I cover this IC right there, I have the second equation that is needed to solve the equation, right? I have IL and VC, right? So now I have two equations, two unknowns, two differential equation, two unknowns. And you could definitely reduce the two equations into one equation with one unknown, for example, by taking the first derivative of, let me erase this, of the second equation. Right? If you take the first derivative of this equation, you get dIL dt, right there, equals the second derivative of dvc dt. See that? What do I do with this? Well, if you look at the first equation, what can you do with that new equation? I could substitute, right? That's the dIL dt equation. I could substitute that back into the first equation. That way I could get rid of IL. So now you end up with one equation, one unknown, which is VC right there. That's the unknown. Okay, and I'm not showing you how I find the solution. That's part of differential equation that you learned a long time ago. So I'm going to go straight to the solution, right there, right? Because we have one equation, one unknown, you should be able to solve for VC, right? And there's the equation for VC right there. That VC is equal to VS minus VC naught cosine of omega naught T plus Z naught IL naught sine of omega naught T. First thing that we can learn from this equation is that this proves that the resulting capacitor voltage is what? Anybody?
Sine wave.
It's a sine wave, right? With respect to time, right? Varies with respect to time, and the shape follows a sine wave, as you can see from the cosine function and the sine function, right? Number two is that this equation depend on, or is affected by, I should say, several things, right? Aside from, of course, the given values, VS, that's usually given. It is also affected by, for example, VC naught. What is VC naught? VC naught is the initial condition of the capacitor. So imagine if the capacitor has initial voltage, then we call that initial voltage VC naught, right? Turns out that this equation also depends on IL naught. What is IL naught? That's the initial condition of the inductor. So if the inductor has an initial flux, right, and then translate it into current, IL naught, then that IL naught appears in this equation. Okay, and then what about omega naught? That's another parameter in the system. Well, that's our resonant frequency. Right? Notice that it is in omega, not F, right? So therefore, the equation is 1 over square root of LC. Right? So that omega naught is a function of the quantities of inductance and capacitance in that circuit. Okay, and lastly, we have Z naught. That's another parameter that would affect the equation or this or the behavior of this waveform, right? What is Z naught? Z naught is called characteristic impedance, right? Which is equal to L, the square root of L over C, which is the same equation you learn in electromagnetics, right? So it's the same exact equation, square root of L over C. All right, so any question on this first equation? So now you know the process, right? You have the circuit first, and then you derive the equations. Now you have two differential equations, two unknowns. You reduce it into one equation, one unknown, and then you're able to solve for one of the parameters, in this case, capacitor voltage. And then how do I know the second unknown? Well, once you know V of C, what do you do with that? Well, you can go back to the original equation, for example, right? Let's say this one right there. What is it? Yeah, you can do this equation right there, and you can see that IL, if you want to look for the equation for IL, is equal to CR, right? The resonant capacitance times the first derivative of this equation, VC. So if you do that, you get the equation for IL of T right there. Okay. Again, just like capacitor voltage, this equation has IL naught, which is the initial condition for inductor, VC naught, which is the initial condition for capacitor, Z naught, characteristic impedance, omega naught, resonant frequency. And just like the first equation, this also proves that current around this loop, right, current through this loop is a sine wave, right, as demonstrated by the simulation result I had earlier, right? So these are mathematical proof that both waveforms will follow sine waves. But then the next question is, right, if we want to use this circuit, right, into our DC to DC converter, then we want to make sure that regardless of initial condition that we have inside each of these or both, right, it should still be a sine wave, right? Because again, the key on getting soft switching is to be able to get the sine wave, right? So I want to make sure that it doesn't matter what initial condition you have on each of these components, L and C, I would still have a sine wave, either the current or the voltage or both, right? So how do I do that? Well, let's take a look at, that's why having this mathematical equation will be convenient, right? Because that we could actually easily prove that by using these equations, right? So for example, before I do that, how many cases can we, that we should look into? Well, we have two different components, right? And each component could have initial condition. So therefore, we're going to end up with 4 different possible states of, 4 possible conditions, I should say. Number 1, L and C both have initial conditions. That's the first case we need to look into. And we want to make sure that if both L and C have initial conditions, then the waveforms are sinusoidal for both voltage across the cap and current through the inductor, right? That's the first case. The second case is when both L and C do not have initial conditions, right? If that happens, again, we want to make sure that we end up with sinusoidal waveform for both capacitor voltage and inductor current. What is the third one? Well, the third one would be combination, right? Maybe you have initial condition on L, but not on the capacitor. That's the third case. And then lastly, the other way. No initial condition on L, but then you have initial condition on C. In any of these 4 cases, we want to make sure that we always end up with sinusoidal waveform for both capacitor voltage and inductor current. If we are sure that we always end up with a sine wave, then we should be able to use this into our DC to DC converter, right? Without having to worry about initial conditions, okay? So let's do that. Let's do the first case. What happens if both L and C have initial conditions? Well, those are the equation in front of you, right? This shows you that if we have both initial conditions, VCO and IL, VC naught and IL naught, then you end up with sinusoidal voltage for the capacitor and sinusoidal current through the inductor, right? With IL naught and VC naught. Agree? Okay, then what happens if we have no initial conditions at all on both L and C? Well, you can also look at these equations and just apply VC naught equals to 0 right there, and IL naught equals to 0 right there, right? What's going to happen if VC naught and IL naught are both 0? Do we still have sinusoidal equations? Yes or no?
Yeah.
Yes, right? But the equation number 1 becomes Vs minus Vs cosine of omega naught t. So it is still a cosine function with both initial condition to be 0. Is that clear? What about the IL equation? Do we still have sinusoidal waveform if both initial conditions are 0? The answer is yes again, right? Imagine if this is 0 and that is 0. So then you end up with IL of t equals Bs over Z naught times sine of omega t. Again, we have sinusoidal waveform for the current. Right? How about the other 2 combinations? Well, that's what I have right here. Right? No initial conditions. Right? Those are the 2 equations, sine waves, right? And then when you have non-zero initial conditions, that's the 2 equations that you saw earlier. And then this is the simulation results for what? VC has 0.5 volt and IL has 0.25 amps, so both initial conditions. Right? And then number 3, when only C1 has the initial condition. If that's the case, equation number 2 reduces to IL of t, and you can see still is a sine wave. And then VC of t reduces to that equation right there. Still a sine wave, right? And here's the proof, right? So you have VC initial condition, 0.5, IL 0, both are still sine wave. And then lastly, the last combination, you have, what is it? Only L1 has the initial condition and C doesn't have any initial condition. So you can see you end up with still sine wave functions. Pretty cool. So you get sine wave for both capacitor voltage and inductor current with this condition right there. Right? So now I've already proven to you that for series resonance circuit, right? So LC in series with DC supply, it does not matter what initial condition you have in any of the components or both, then you always end up with sine wave. That's what we're looking for. That's good news. What about the other types of resonant converters? Here's another one, right? Again, you have LC, but here you have 2 independent sources, right? VS connected to LC this way, and then in parallel to capacitor, resonant capacitor, we have this current source, right? Please try to remember this resonant converter, because this is the one that we're going to use the first time for the first topology that we'll be learning this week. Is going to have this resonant circuit. Right, so you can see that here we have a resonant circuit that has 2 independent sources, and if you do the same derivation I did earlier, just apply KVL, KCL, right there, you have 2 equations, 2 unknowns again, right? And don't forget that IC is equal to CdV CDT, even though I didn't actually write it down here, but keep in mind that you have DC inside IC. So again, 2 equations, 2 unknowns. You can reduce it to 1 equation. I won't go through this in details. And at the end, you have the solutions for inductor current and capacitor voltage. Just like before, you can see clearly that the inductor current waveform as well as capacitor voltage waveform are both sine wave. And go ahead and do the 4 different cases. I'm not going to go through that, but go ahead and do those 4, and you'll find out that it doesn't matter what initial condition you have for those components, you're going to end up with sine wave. So please do that. Prove it yourself that this resonant circuit will also always give you sine waves for both capacitor voltage and inductor current, regardless of initial conditions. Same thing with this one right here. This is called parallel resonant circuit, right? This is one of the basic resonant circuit you learn in 212. You have capacitor in parallel with inductor, in parallel with current source. Again, you have KCL, KVL right there. And 2 equation, 2 unknowns. Same as before, solution to it, solution to these 2 equations. And we get the solution for that circuit that shows that, again, inductor current and capacitor voltage are both sine waves. And please apply the 4 different cases again, right, to prove that they are indeed giving you sine wave regardless of initial conditions. Any questions on that? Let me stop right here first and stop sharing first. So those are the concepts behind soft switching, is to be able to use resonant converter. Okay? Why? Because resonant converter ensures that we're going to get sinusoidal waveforms. What is the significance of having sinusoidal waveforms? Anybody, if you've been following my...
You have a 0 current crossing point where the power loss during a switching transition would be 0.
Right. Almost correct. What you're going to have is, just like you said, sine wave, but it does not guarantee that current will cross zero. It will guarantee that current will inherently, right, goes down, right? But if you, that's why I'm asking that question. So you'll
If it's
guarantee
like
that.
too little, basically, will it just not approach zero?
Yeah, so you can see that you have to be careful of the offset, right? Because yeah, the shape is sinusoidal, but if you have a certain offset, then it's kind of useless, because then that current will never cross zero. Let me look at an example, a good example to show this. I thought I have it somewhere here. What is it? What happened? Oh, right here. Oh, not that one. That one goes to zero. Are there any pictures where the offset is not? That one also goes to zero. Oh. Well, it looks like all the examples I have, they're all crossing zero. Yeah. Okay, but oh, maybe more. No, I think that's it. But imagine, okay, imagine if I go back to this picture right there, right? Imagine if you have an offset in the circuit, whereas this green sine wave goes like this, right? It's still sine wave. That's good, right? That's a good starting point, but it's kind of useless, right? Because this minimum point doesn't even reach zero. Right? This is the zero line right there. Okay. So if let's say you have, goodness. So having sine wave is very important, but you want to also make sure that that sine wave, right, crosses zero, right, like that. If that sine wave is up here, right, then you would never get 0 amp, right, or 0 volts. Does that make sense? Yes. So that's why paying attention to offset is important as well. Any question on that? All right. And that becomes important when we look at our first topology, which is next. But conceptually, is that clear?
Yeah.
All right, good. Let's look at our first converter. Then I'm going to skip this. These are just saying that there are different types of soft switching converters, resonant converters. I'll let you read through this. That's a lot. That's a lot. There's so many of them. And just like buck and boost, right? In EE411, I told you that if you understand buck, then you understand boost, buck boost, right? Flyback and so on and so forth. Same thing here. If you understand ZCS and ZVS, I'm going to go over ZCS and ZVS. So ZCS stands for zero current switching. ZVS stands for zero voltage switching. Buck, so both of them will be buck converter. If you understand these two, how they operate and how we can apply the concept of resonance into the circuit, then it doesn't matter what other resonance circuits you come across. It'll be the same type of analysis, same type of approach, same type of methodology to look at the circuit, okay, or to understand the circuit. All right, so let's start this one. Okay, this very first one is called zero current switching resonance switch buck converter, right? It is a buck converter. From the transfer function point of view, we're gonna derive it on Thursday. But if you look at the structure or circuit configurations, you can see this is a buck. How do I know that? Well, at the input, that's why 410 is important, right? you have a switch at the input, and then you have inductor at the output, and then the diode in the middle, right? So if you look at these three component right there, that's the T network, right? The T network that you learned from EE410. Guess what I'm adding into this circuit? What do you call this circuit?
A resonant
circuit, isn't it, right? So that's our resonance circuit. So just by adding the resonance circuit, small inductor, small capacitor, these are all small components, but of course can handle the power. Then you can actually get soft switching, right? But before we analyze the circuit, so very first step is to be able to analyze the circuit, right? Before I do that, I want to make some assumptions to simplify the analysis. Right? Number one, I'm going to assume, this is on the following page, right? The assumptions. Number one, if I can remember all of those, number one is that I'm going to assume that every single component is ideal, right? So no loss, no drops for now, just to simplify the analysis, okay? Ideal components. Number two, we are going to operate this converter at very high switching frequency, right? We should be able to do that because there is no overlapping, right? And so because it is a very high switching frequency, then imagine the ripple going to this inductor. It's going to be small. Pretty much this is going to be flat, right? If this is pretty much is flat, then this is basically going to be disappearing from the circuit, right? No AC component will flow through this. Very minimum amount, very negligible amount of AC current flows through this, right? So if this is flat, then I could replace the whole thing with a current source. You agree with that? Again, if we operate this converter at very high switching frequency and enough inductance, of course, to make it almost flat right here, that means I could replace all these three components into just a current source, right? Why? Well, because we always have voltage across here, right? We always have voltage across the output, and that's required by the load. In our case, is RL. So therefore, by Ohm's law, voltage that we always have at the output of this converter divided by R gives you current right there, right? And that current should be flat so that I can model it as a current source. Does that make sense on that assumption? Any question on that one? All right. The third assumption is that in order for this circuit to work, this switch has to be unidirectional. What does that mean? Anybody? Unidirectional means?
One way.
One way, exactly. So we cannot have, or we cannot allow current through the switch to go from right to left this way. That's a no-no. If you have this, then this circuit does not work. Okay, so you have to have a unidirectional switch for this to work. I believe that would be it in terms of assumptions. Okay, so if I apply those, especially the output stage, I'm modeling the output stage as a current source, then this circuit reduces to this circuit. Yes? Good. Right. Then note that it is actually important to note that the switch right there is in series with inductor, resonant inductor. We have two inductors, okay? So don't forget, these are two different inductors. We have the big inductors right there, and we have the small resonant inductor. Right? As you can see, the switch is in series with the resonant inductor. So if we can somehow resonate this inductor with the capacitor, then we know from the previous section that inductor current is going to be sine wave, right? If this inductor current is sine wave, since switch is in series, therefore switch current will be a sine wave as well. Okay, so that's the trick right there. Any questions so far? I'm going to do this slowly. Okay, there's no questions. Next, let's see. We have two different switches here, right? Switch, the main switch, and the diode. In EE411, when we talk about a buck converter, do you remember how many states of the circuits you have? How many states of the circuit you have in a regular buck converter? Come on. How many states?
Right.
Two states.
Just only two states, exactly. When the main switch is on, and then when the main switch is off. That's it, right? 2 states. Here, since we are dealing with soft switching, the downside is that in soft switching, you're going to end up with more than just 2 states, right? In this example, you end up with 4. Can it be more than 4? Absolutely. If you look at other topologies, sometimes you end up with 8 different states. So more complex analysis, right? But again, even though those are many states, but individually, every state, it's going to be, the same thing over and over again. It's going to be not resonant, and then followed by another resonant, things like that. So it's going to be pretty much similar to what we're going to be learning from this topology. So that's why the key, it is important for you to be able to understand this topology before you can understand the next one. Okay, before we can learn about the next one, I should say. Right. All right, so we have the main switch and we have the diode as another switch. So we're going to end up with 4 different states for this topology. All right, the first one is when the switch is on, diode is on. Right, that's the first one, right? Because we have two switches, therefore there are 4 combinations. And then we have switch on, diode off. Right? And then we have switch off, diode off. And then we have switch off, diode on. Right? So 4 different states. These are the pictures for each single state. Right? The first one right there is when the switch is on, diode is on. Here, switch is on, diode is off. Here, switch is off, diode is off. Here, switch is off, diode is on. Okay. Now, also one thing that I forgot to mention is that it is also important to note that the resonant capacitor is in parallel with the diode. You see that? That means if the diode is conducting, right? If this diode is conducting, assuming ideal diode, that means voltage across it is equal to 0. Yes. So this is basically a short. Okay. So anytime diode is on, what's going to happen with this resonant capacitor? It's practically not there, right? It's not doing anything. It's being bypassed by this short, right? So that's important to note, okay? So we're gonna see that in this in one of the states, or maybe 2. We'll see. Yeah, 2, I think. All right. So let's start with our first state right here. Now, this happens after the circuit reaches steady state. Okay? And it doesn't matter how you or where you start in terms of which state you want to start the analysis. Right? I randomly pick this state right here, where the two switches are on, right? The switch is on, the main switch is on, the diode is on. So that's what happens here. And then in the meantime, or at the same time, I should say, I'm also going to draw voltage across the capacitor as well as current through the switch. So what is my pen? Oh, right here. So I'm going to start the analysis at times equal to 0 seconds, okay? All right, and here's VC, and here's IL, right? VCR meaning resonant capacitor voltage, and ILR resonant inductor current. And the waveforms are in the book, but I'm gonna draw them again here to clarify the concept, right? Okay, so I'm gonna start with this state. Again, it doesn't matter where you start, but I'm going to start with this one. So this one is when switch and diode are both on. Okay, what happens if both switch and diode on? Well, look at the original circuit first, right there. If diode is on, that means this capacitor is practically out of the circuit. It's useless, right? That's why I don't draw the capacitor there. It's not doing anything anyways, right? And then right now the switch is on. So remember, switch is on, diode on. So here's the switch. I didn't draw it, but the switch is actually a short. So now you can see that supply voltage is in series with the inductor and the switch that is conducting right now. So basically, this is the circuit that you end up with if the diode is on and the switch is on. Any question first before we go into the math? Okay, now let's do our KVL, KCL. If you look at this circuit, just focus on this one for now, okay? Focus on this one. Let me make it bigger. All right. Now, if this is a short, by KVL, you can clearly see that if this is a short, then voltage across the inductor must be equal to supply voltage, right? That VL is equal to VS, right? So if that's the case, if you agree with that, VL is equal to VS. Again, this is in the book. You don't need to take note on this. And I know that VL by itself is L dIL dt, right? Is equal to VS. And so therefore, dIL dt is equal to VS over L. You agree with this equation? So as soon as the switch is on and diode is on, I'm exposing supply voltage, the entire supply voltage across the inductor. And that would cause the inductor, right, to have a voltage of VS, and that would cause the current through the inductor to follow the slope right there, right? dIL dt, that's the slope of inductor current. What can you say about this slope? Given VS is positive, L is positive. What can you say? What do you think is the shape of the waveform or current through this inductor? What is the shape?
Sinusoidal.
Sinusoidal? Remember, this is the slope. So you need to first know what is the slope there. Is it a sine wave? Is it following a sine wave? Well, first of all, I don't think this is a resonant circuit, right? Because it doesn't have a C in it. It's just inductor, there's no C, right? So for sure, this is not a resonant circuit, not yet, right? But based on this equation, if Vs is constant, right? Typically it is, right? Constant, and then positive, and L is also constant and positive. So therefore, the slope is going to be positive and constant. So what's the shape of the current then, if it's a positive and constant slope?
Linear.
Linear. So you can see that if I start from 0 second, if I draw the inductor current starting from 0, as soon as both diode and switch are turned on, I should say, then inductor current start with linear shape, right there, linear shape. dIL dt is equal to, the slope is Vs over L. You agree with that? All right. What about capacitor voltage? That should be easy. What is the voltage across this cap? Imagine there's a cap across it. Well, that should be easy, right? That should be 0 because that's right across the short. So if I were to draw the capacitor voltage, that's going to be 0. Any question on that? No? All right. Please interrupt me, okay? If anytime, as soon as you see things that are not making sense, let me know. All right. So what I'm saying from what is this? Well, what this circuit is showing us is that as soon as we expose Vs, a constant voltage across this inductor, then current through the inductor grows linearly, right? Linearly, and there's nothing to stop it, right? If you look at this circuit, there's nothing to stop that current, right? It's going to go linearly. It's going to grow up, right? Linearly, it's going to go up linearly. Until when? What stops it to become, to growing linearly? What stops it? Well, by KCL, right? If you do KCL around here, oh, not around, sorry, KCL at this node, right there, what does it say? IL is equal to, sorry, IL plus ID is equal to I naught, right? If you do KCL on that node. Well, imagine that, IL is increasing and I naught is constant. So IL plus ID is equal to I naught. I naught is constant. IL is increasing. What can you say about ID?
It has to be decreasing.
It's changing.
Decreasing, exactly, because again, I out is constant. By KCL, the sum of inductor current and diode current has to be zero. It has to be equal to I out, and I out is constant. So if inductor current is increasing, to compensate for that, ID would have to be decreasing. Until when? Until ID goes to what?
0.
To 0, exactly. So this current IL increases, right, linearly until it hits I naught or I out, right? At which point ID must be equal to 0. Yes? When ID is equal to 0, what happens? Diode turns off, right? When diode turns off, if this one turns off, open, right? Then what's going to happen? Capacitor shows up, right? Look, now it goes to this state right there. As soon as diode is off, capacitor shows up, right? And so if I draw that inductor current, right, it's going to keep increasing until it reaches I naught. So let's say that happens at t equals to t1, right? Right there. Okay, right at t equals to t1, when IL is equal to I naught, ID is equal to 0. So now capacitor shows up, and guess what you have now? What do you call this circuit? Remember the one that I asked you to memorize? Not memorize, remember from earlier section? What do you call this circuit? Anybody? You don't remember? Here, I'll show you again.
Series resonance with parallel load.
Yes, right here. See that? It's exactly the same as that circuit, isn't it? And what can we know about this circuit from the previous section? What can we know if you have this circuit? That inductor current will be what?
Sinusoidal as well as capacitor voltage.
Exactly, exactly. That's why, to me, this is really clever, right? Because as soon as diode is off, naturally the circuit changes its state to a resonance circuit. Cool, huh? Because once you get into resonance circuit, guess what happens with IL here? It doesn't follow linear shape anymore. Now it's going to be sine wave. Right? Same thing with capacitor. Will be sine wave. Maybe I don't draw it correctly there, but something like this. Okay, it's going to go to a sine wave state. So it's going to be sine wave. So it's no longer linear. This is linear. But right after T1, right, IL follows sine wave. And what's good about sine wave? It naturally goes to 0, right? So if I allow this resonance circuit to occur, right, at some point of time, this IL, which is the same as I switch, keep in mind, okay, because they're in series. This IL is going to be a sine wave, and then that current through the inductor eventually will go to 0, right? Assuming what? Assuming we have the proper offset. So if this sine wave is sitting right here, that's useless, right? So we want to make sure that this sine wave will eventually hit 0. And let's say if I let it to continue, if I let the sine wave to continue, then it's going to go like this, right? Let's just say. But you'll see later on that it's not going to happen, right? It's going to stay at 0. Okay, so that's what we're aiming, is that in the second state, inductor current, oh, wrong one. Inductor current is a sine wave, and so is the switch current. Capacitor voltage is also a sine wave, right? And we wait until the inductor current goes to 0, and when it reaches 0, then what happens? Imagine if, I'm going to erase this, right? At this point, this inductor current, right, follows the sine wave, and at some point of time, it crosses 0, and it tries to go negative, right? it will try to go negative, just like a sine wave. It tried to go negative. But can it go negative or no? Can the inductor current goes the opposite way from right to left?
No, because we're assuming it's unidirectional.
Exactly, very good. You've been paying attention. Yeah, because the assumption that we made is that, or what I said earlier is that this topology can only work if the switch right there is unidirectional. Now you know why. We don't want to allow this inductor current when it's resonating. We don't want to allow this inductor current to flow backward. We want to stop it. So therefore, if I go to this picture again, as soon as the inductor current or switch current, this is IL equals to I switch, it goes to 0, then it will stay at 0. Okay? All right, now tell me, when will be a good time for us to turn the switch off? If let's say this is equal to T2, when will be a good time to turn the switch off?
T2.
When?
At T2.
At T2 or anytime after T2?
Or just exactly T2, because then the current will be negative and then you'll get a negative voltage spike across the inductor.
Well, current cannot be negative, right? Current is being clamped at 0. So remember, IL is equal to I switch, right? And IL or equal to I switch cannot be negative. So it will be staying at 0. Does that make sense?
Kinda.
Okay. All right, so then now that we know that a switch current stays at 0, then now I know that any time after T2, right, I could turn the switch off at 0 current.
Wait, is it by KCL that it just stays at 0? Because wouldn't it just oscillate? Why doesn't it continue oscillating down again?
Well, because the switch is unidirectional.
Oh, unidirectional. Yeah, that's right.
Right? Yeah, that's why it is important for you to have a unidirectional switch. Otherwise, this won't work. Right? So because of the unidirectional switch, that current stays at 0. And
so basically automatically turns off at time at T2, like it's effectively off.
Well, the switch can still be on, right? The switch can still be on, but the current is 0. Its current is 0. So
the switch is on if it's forward though, but like we talk about like a diode being off if it's reverse biased, right? Like, is it the same type of thing?
No. So this current right here, as you know, is sine wave, right? And it will reach 0, right? And it will try to go negative, but it can't, right? Because of the switch being unidirectional. And so that inductor current can still be at 0 while the switch is still on. I can still have the switch conducting, not conducting, but on, but it's not conducting any current.
It would have infinite ohms though, right? In the revert. Because like voltage would be, or would V equal Vs?
No, that voltage is going to be appearing across here, right?
But nothing across the end. Oh, because the current 0.
Yeah, the current here is 0. Right now, there's no current at all here, nothing. But doesn't mean that the switch is off. I can still have, the high pulse into the gate, right? Even though the current is 0.
Oh, so that's what you're referring to when it's on, is basically if it's allowed to conduct, if it's going in the right direction.
That's correct. Yes.
Okay. That's what I wanted to clarify.
Yeah. So at this point, right, I can still have the switch still on, but right now it's conducting 0 amps at this at T2, right? So
but it's not acting like a short circuit, like an on switch.
No. So the gate is still active. The gate is still active. It's still high.
Okay, so if gate is active, switch is on. If gate is inactive, switch is off.
That's correct.
But only conducts in one direction.
That's correct. So
okay.
Yeah, physically the switch is still on, but it's not carrying any current. That's why.
Could it be modeled by a regular bidirectional switch in series with the diode?
Yes, exactly. You could do that. So you could do a diode and then a bidirectional switch like a MOSFET. Yes, you could. Definitely. That way it prevents current to flow backward. Okay. But yeah, so the point is, you know, once the current through the switch is equal to 0 and the switch is not off yet, now let's say over here, and then we can adjourn. Let's say over here, I can turn off the switch, right? Let's say that the switch is conducting, this is the gate to the switch, right? The gate signal. I could have the gate signal high, right? This is high, this is low, all the way to that point, right? Let's call it TX, right? You can see that from here to here, the gate signal is still high, meaning the switch is still on, but it's not conducting any current. It's just 0 amps, right? Because from this waveform, we know that current is 0, right? And then after that, right, at this point, I could just turn off the switch at 0 amps. Does that make sense or still confused?
Makes sense now.
Yeah, so as the switch is carrying 0 amps, now I'm gonna turn off, boom, turn off, right? Gate down. Now, by doing so, I'm achieving ZCS, zero current switching at turn off, right? And so it doesn't matter what voltage you have across the switch, right? Voltage times current will always be 0, right? Because current through the switch is 0 amps. Okay, I'm gonna stop right there. I'll let you absorb this, and I'll repeat this analysis on Thursday, so that you can ask question hopefully on Thursday if you're still confused. But again, the idea there is that, you know, wait until current through the switch is 0, then you turn it off, right? If you do that, then it doesn't matter what voltage across the switch is, right? You have product of voltage and current equal to 0, so no switching loss.